Hi guys, welcome back to my channel as we dive into one very important topic, and that is precipitation. How do we get the precipitation data? How do we compute it? And then how do we create some awesome 2D and 3D maps of precipitation for a given area? All right, folks, our first step is to install and then load the packages that we need. This is pretty easy because we'll be using the pacman package for that purpose. And the first thing we need to do here is, first of all, check if this package is actually installed on our system. So then if it's actually not installed, we need to install it, and installing it is using the Bezier function install packages and then pacman. So the good thing about pacman here is that it's going to help us install and load packages using just like one line. So here I call pacman, and then I call also pload, and then I can simply provide the names of the packages that we need. The first one that we'll be using is the pRecipe package, which allows you to download 27 different datasets on precipitation, and we'll be using one of them in today's tutorial. The next one that we will use is GISCOR, simply for downloading the shapefile of a certain country for which we will get. We'll be using heavily here Terra because we're working with a raster file. We definitely need the umbrella package tidyverse for data wrangling, but especially in this tutorial for data visualization because we'll be using ggplot2 for that purpose. And then also for data visualization, we'll be using rayshader package. Okay, so in the next step, we will select simply the country extent that we'll be using then to crop the precipitation global data. And to get the country boundaries, it's pretty easy. So we can use simply GISCOR, which we previously used. And there's a function which is GISCO get countries. And within this function, we need to specify at least two attributes. The first one is the country. So here we pass the ISO2 or ISO3 code. Let's take, for example, Switzerland. And then for the resolution, so this is how crisp the detail will be. So let's take the crispest one, since anyways, it's territorially a small country. Downloading precipitation data with pRecipe is ridiculously easy. You just need to use one single function, and that will download the data onto your local drive. So let's actually call pRecipe, and I will show you in practice how this looks like. There's a function which is called download data. So this is going to download a data set to your local drive. And here you need to choose what kind of data set you want. If you're using VS Code like me, you can simply hover over this download data, and this will show you the acronyms for different data sets. So here you can see there is ERA5, there is EMERV, there are different ones. We'll be using this MSWEP, which has a very crisp resolution, 0.25 degrees. It's for the global extent and goes from 79 to 2023. So let's actually write this one right here. So you need to use the acronym MSWEP. All right, the next one is the pathway. Because we'll be downloading, you need to provide the working directory, and here I'm choosing the main working directory. Then the domain one is optional, so this one is whether you want a global local data or raw. Raw is simply a default. It's going to give you the one that is available for this data set in particular. Global level is available. And then the last one is called timestamp. This is the temporal level of analysis that you want to take. There are two possible, monthly or yearly. And here I'm going to go for a yearly dataset. Once the download completes and you inspect your main working directory, you will see the name of this NC file. So this one contains the name of the dataset, then the name of the variable, which is TP, meaning total precipitation. In millimeters, it's a global extent and goes from 79 to 2023, 0.25 degrees, and on the yearly level. All right, folks, now we have the file name and we can use Terra to load it here. I'm just going to create a new object, and then I'm going to use a Rust from Terra, and here I'm going to pass the name of this file. And before actually we proceed, I would like to show you the properties of this file. So I'm just going to actually expand this, and I'm gonna quickly print the details. You can see here that the dimensions of this one are not that big, but it does have 45 layers, where each layer is the precipitation data for a single year. The resolution is 0.25 by 0.25 degrees, as I said. The extent is for the entire world, and the coordinates reference system is WGS84. This is, of course, the name of the file that we just loaded. The variable is, of course, precipitation. and the names actually correspond to each year. Here they are actually they use numbers to denote years, but basically this starts from 79 and goes all the way to 2023, as you can see here also from time. One thing that can confuse you here, so this is not a monthly level, this is the annual level, and the units are millimeters of precipitation. Okay, now that we have this, we can simply work off this one and then use crop function from Terra to basically just crop this for the extent of Switzerland. So we can just pass here country SF. Now, if you want to just quickly and dirty visualize this, that's going to be easy. Let's use here plot from Terra, and let's pass this one that we just created, of course, because this is the list of 45 different layers. We can simply take maybe the first one. So this will be the 1979. And then we can also add as an additional layer the country boundary so that you can see how this looks like. So here we're using actually SF package, which we didn't install and load at the beginning. So I do suggest that you pass it to that first chunk that we have. I will definitely include it in the script in the GitHub repo. So don't worry about that. And here we can just pass country SF. And the final step here, say that we want to add this layer to the plot. And then once you actually run this, you will be able to see the precipitation data for the extent of Switzerland and of course the country borders overlay. Oftentimes you might want to visualize precipitation over time and then to create a map for every year. And this is the first thing that we will do. In order to do that, we first of all need to change the layer names of the raster file. For now, they are not really, you cannot really understand them. So we're just going to use names function. And then we're going to pass our object. And then here we're just going to say, okay, this goes from 79 to 2023. And this is going to change actually the names. And I can actually show you how this looks like. So I just ran this. And once you show the data here, you can clearly see that now names are 79, 80, 81, etc., going all the way to 2023. Okay, so now that this is done, the next thing we need to do is transform this raster format into data frames so that we can plot it using ggplot2. So let's create a new data frame here and let's pass this data into a pipe. And then what we want to do here is first of all transform into a data frame using this base R function. And because we want also the coordinates to be returned, we also have this. Okay, so then we actually run this. And once we run, I also want to show you here what we got here. So I'm going to inspect here a first few rows of this newly created data frame. And what you will see here is that years and year values were coerced into columns. And this is not a good format for ggplot2. So this wide format is far worse than the long format. So long format, which we want to have, is basically creating two additional columns, one which is going to denote year and another column which is going to denote for every coordinate and every year what was the precipitation value. Okay, in order to do that, that's fairly easy because tidyr package, which comes from the tidyverse, which we loaded before, has a function which is called pivot longer. So we are now pivoting. And one thing that we want to exclude from this pivoting are those two IDs, so X and Y. And this is actually going to exclude them from this operation. The next thing that we want to do is create that year column. So this is going to be handled using this names too. And then we're going to call it year. And then the final one is the value column, which is handled using this values too. So how do we want to call the value column? We can call it, for example, precipitation. Okay, so then we can actually rerun this. And once we rerun, I'm going to show you now the first few rows and what we actually got here. So you can now see we tidied up this a bit, and now we have only 4 columns. So this is now in a long format, and this is good to go to work with ggplot2. But before we jump into that, one thing that I want to clarify here is I found that the data for 2023 in this dataset is not complete, so it's not for the whole year, which actually is going to bias our results if we include 2023. So I decided here to filter it out, and I can use for that the plier filter. And simply what I say here is that I don't want to have where year is 2023, so exclude rows that have 2023. We can now lay the foundations for our ggplot2 by creating a theme, breaks, and colors that we'll be using in our panel map. All right, so for the theme, what I like to do is I like to create a function, and which is called theme for the win, obviously. And then within this function, then I like to define the elements that we're going to use. Now, obviously, if I didn't create a 3D map, I would be just using theme void as a start. But because we are using rayshader and it doesn't handle yet the theme void, we need to stick to the theme minimal. And then within theme, we can then define other things that we want to exclude. So the first one is excess line. So we don't want any excess lines. So to exclude in ggplot2, you simply say that this is element blank. Then we can also exclude the titles. That can also be element blank because we don't want the title. So if you actually want to have X and Y titles or something like latitude and longitude, you can actually keep these, so they should not be here declared as element blank, but I do like to exclude them. Also, if you would like to exclude here the coordinate numbers, you will do basically the same thing that we did here, so you declare it as element blank. Again, if you want to keep the coordinates on your plot, you should not be writing this x's.xy, and also you should not be writing the one for X, because this is gonna exclude them. They're not gonna be on the plot. Okay. Then there are several things that we are not excluding, but we are defining. And then one of them is the legend position. So I would actually like to position legend on the right hand side. This is just a matter of preference. It can be also the top, bottom, or left hand side of the plot. When we are here at also the legend side, we can also define the legend text and legend title. And because this is text, we need to tell ggplot2 that it is text. So I'm here writing that this is element text. And now over here, what you can define is, for example, size. So we can go for a size 11 pixels. We can also define the color. Again, a matter of preference. I just like to keep it simple. So like charcoal gray. And you can also define other things here, like for example, the positioning, the vertical, horizontal. What we did for the legend title, I'm just going to copy here, and we can define also the legend text. So these are going to be the numbers. We can make them a bit smaller here, just like this. And again, you can here define also other things. Now, because we're using Team Minimal, there are also all these panel grids and plot grids and legend grids that we also want to either get rid of or kind of define a certain value for them. So the first one is the major grids here, which we want to define in a certain way. So this is actually a line. So we want to tell elements that this is line to ggplot2. And then what we want to do here is we want to get rid of the color of the line. So we're just gonna say that the color line is basically missing. It's more or less saying like this doesn't even exist. So I didn't check with element blank how it would work, but this is something that I already checked, and it's working just fine. We also need to do this for the minor ones. Again, if we use the theme void, we wouldn't need to do this, but again, later on, rayshader is simply not going to work with as well. There's also plot backgrounds, and this is a different element. So this is a rectangle. So there is a special here attribute, which is called element rect. And with this one, we can also get rid of both the color and the filling of this one. So both the color and filling is equal to NA. And there is also something which is a legend background. Now for the legend background, I do want it to have its, once we go, of course, the 3D creation, I want it to have its own shadow a bit. So I'm not actually gonna fill it with NAs. I'm gonna assign it a white color for the filling, but the borderline can actually be NA as well. Okay, and there are also some other things that are left here in this area of defining these borders. And this one is the panel border. So the panel border is also the rectangular element, so I'm just going to copy it here. But here we are just going to go for this solution, which is filling and color are going to be omitted. Okay, so once this is done, we can also define the plot margins, which can come really handy, and I usually apply this in all of my tutorials using ggplot2, because simply it allows me to shrink the white space, blank space around the map. And how do I do that? I simply define the top side, the right hand side as 0, though here maybe for the right hand side we could even give it a bit more space. Anyways, we'll just keep it like this for now. The reason why it's saying we can give it more space at the right hand side is if you remember, we defined that our legend is going to be on the right hand side. But anyways, let's just try it like this. Okay, and then here we simply need to define the units here, and this is our legend that we will or actually our theme function that we will later on call in ggplot2 while creating our 2D maps. For creating the breaks, I like to use natural intervals because they rely on the data distribution to create the breaks. And for that purpose, I use the class int package, which we didn't call at the beginning. So I'm actually in the final script, I will add it back to the pacman, and I'm gonna also install it and load it if it's not there. But for now, we can simply call class int, and from class int, there is a function which is called class intervals. We use it in so many other tutorials beforehand because it's so useful. So over here, what we need to provide is the name of our data frame, of course. And the second thing we need to provide is the name of course, the column from which we are taking the values. So in our case, it's precipitation. So that's the name of the column. Okay, once we define this, we can then define how many, of course, breaks we want. I'm going to put here 5. Doesn't mean it's going to be 5. It, again, depends on the distribution of your data. Maybe it's going to be 4, maybe it's going to be more than this. You can always check that. And finally, the style, I like to use the equal spacing, but there are also so many other styles here. As you can see, there's a fixed, pretty, based on quantiles, Jenks, or Fisher formula. So these are different options. And finally here, you want to access, because this is going to return a list, you want to access the part of the list which refers to the breaks. All right, and then once we have the breaks and the number of breaks, we can also define the colors here. For the colors, we can use the base colors. So these are HCl colors. I usually use those. And then here for the number of colors, what we can simply use is the length of this breaks. That's the easiest way you can do. So then it's going to correspond to the number of breaks you have. Now for the palette, you can check different palettes, but there is one which is used for temperature. It's called temps, and I find it really cool because it has the cold colors, which could maybe indicate, you know, the blue and the green. This could indicate higher precipitation levels, and then they're transforming into warmer colors, so yellow, orange, and red, and these can, you know, indicate, you know, less precipitation, so more kind of a drier conditions. And in order for us to have this in a proper order, like we now described, we need to actually reverse the color palette. So I'm putting here that ref equals true. All right, we have all the ingredients and we can finally create our 2D panel map. And this one, I would like it to be a contour map together, of course, with the tiles, because I noticed that this is kind of a standard where you're making rainfall or precipitation maps. So let's start off by calling this map 1 because we'll be making another map after this one. And then let's start with calling ggplot here and defining, of course, the data that we'll be using. So the global data that we'll be using is, of course, this data frame that we created. Then we add the first layer to this one, and because we're using here a raster, we need to call a geom a raster. Within this aesthetics, there are actually 3 columns that we want to use. We want to use the X column for longitude, the Y column for latitude, and then we also want to fill those raster tiles using, of course, precipitation, which is our value column for the precipitation levels. Okay, so there is then another layer, and this one are contours. So geom contour handles this one. So this is going to add a contour lines. And here we again have actually 3 aesthetic values. So 3 values that are going to be painted based on the variable inputs. This one is again X and Y. So these are the same ones. And then the third one is called Z value. And for this one, we again use precipitation. So this is the only difference. All right. And then we could also potentially add here the third layer, which maybe it would be a good idea since we have the bounding box area of Switzerland, not the Switzerland itself. So we can add the boundaries of Switzerland here. And for that, we use geom_sf. Now here, what we do is we use a different data source. So we use that country SF from the very beginning. Then we actually want the filling to be transparent. So in other words, we don't want filling here for the country boundaries. We don't want to fill them with the color because we already have the raster, right? So fill is then transparent, but then we can choose, of course, the color. We can, for example, go for charcoal gray color of the boundaries, or even black. And then finally, we can define how thick this is going to be. I usually go for 0.5 pixels, so that's something that I would go for. All right, so now that we have these different layers, we can go ahead and customize our map. The first thing we want to customize is, of course, what are the colors and breaks that we're going to be using here. So here we use simply scale fill gradient, because we have a continuous measure. This is precipitation, so we need to use a gradient here, or continuous. The first thing we want to do here is the name of the legend. And I'm just going to put here millimeters because we're working with precipitation. So the only thing we want to know here is, okay, so these are millimeters of precipitation. The second argument is colors, and we have this under same name colors. We have actually the values of the colors. The next one is breaks. We already defined breaks, so we are fine. And then I would say one important one is limits here. We want to define the limits so that we have both the lowest and the highest values in precipitation data taken into account while we have these breaks. So here we provide a list of them. So we need the minimum one, so the minimum of our main data, so our main data frame, and then using the column precipitation, of course. The second element, as we said, is the maximum value here, and we simply copy and paste a data frame and the column name. Okay, now that we added this one, what we want to do next is, because we want to create here a panel map so that we have actually different maps for every year put in a single plot, we can use facet wrap, which we also used before in one of the previous tutorials. And here we want to use the year column, right? So for every year, we want to create a separate map. And that's everything you need to do here. Then the next part is guides. This one is going to define how our legend is going to look like. So our main aesthetic here is fill, the raster. So for that one, we're going to define a legend. And because we have a continuous value, we're going to use a legend that is appropriate for continuous values. So the direction of this one, I would go for vertical. Again, you can choose here to go, for example, for horizontal. You can also define the bar height here. So for the bar heights, we can go for something which is kind of a very, I think, like tall or high. So like 50, let's say, millimeters. And then for the bar width, we can go for something that will make this legend a bit thinner. So let's say, for example, 5 millimeters. I think that's going to be fine. You can also here define the legend title position. The legend title position, I would just put it on the right hand side, or actually, sorry, it should be on the top. So it should be above the legend itself. What we can do is we can also define the label position. So this is going to be the text of the legend. And this one I would like to put at the right hand side of the legend plot. You can also define here the horizontal justification of, for example, your title. And I would like to put it in the middle, so 0.5. And you can also define the label, for example, horizontal justification. And this one, because it's on the right hand side, yeah, we can still mid-center it. That's also fine. The number of columns here is only one column because we have a vertical one, and we don't want to stack them together, close together, because this would be for the horizontal legend. So I'm just going to put here that the by row equals false. And then the very last thing here in our code that we need to do is simply add that theme for the wind that we created and run the entire code. And once you run this code, you should be able to see the panel precipitation map of Switzerland from 79 to 2022 inclusive. Okay, this was great, but sometimes we might want to have the average precipitation over a longer period of time. And now I'm going to show you, first of all, how you can calculate that, and then how do you also map both as a 2D and then the 3D map. So we can work off that data frame that we already have, and we can simply average the values using that data frame. So I'm here going to put it into a pipe, and then I'm gonna first of all from dplyr group by, and I'm gonna group by two columns here. I'm gonna group by X and Y, so these are gonna be the IDs. And here I want to say that I want to use both of them as my grouping, so not just the first one, which is X, right? And then in the next one, we simply say, what are we gonna do? How are we gonna summarize the value here? And the value is the precipitation. So I'm gonna create a new value, which is called mean. And I'm gonna use the mean or the average function and then pass to it the precipitation. So this is gonna create then the average values. And let me actually show you how this looks like once we run this. Okay, so once we run this and once I show you this first few rows, you will see that we don't have anymore the year column, because exactly we averaged the data from 79 to 2022. So now we have the X, Y, and then the mean precipitation in millimeters. Now we already have the theme for the wind, but we do still need to apply the breaks and the colors, so to calculate those. So I'm just gonna actually go back over here and simply gonna copy this and paste back here. So both for the breaks and the colors, we of course need to do some minor modification in terms of the name, of course, of the data frame. So this is different, and of course the name of the column here is now mean. So we can actually run this. We can run this one. Now for the colors, it's going to be the same because we're simply using here the breaks argument, which we previously, created. And then for the colors, I'm going to actually stick to the same color palette. Okay, now once we have this, what we can do is we can simply create our 2D map. Now, again, what we can do is we can work off this one. There is no purpose that we now rewrite the code again because it's quite similar. What I'm just going to do is I'm going to rename the main object. Of course, it's going to be map 2. I don't want to rewrite the previous one. And then, of course, here we need to change the names of the data. Okay, so the first one is, of course, this average DF data frame, which we're going to use. Then the name of the fill value here in the GM raster, it's going to be called mean, of course, because it's used in this data frame. Then if we go to the GM contour, we also need to change here the Z value. So it's going to be also called mean. This one can stay. So the country borders, that's totally fine. There's nothing to change there. Here, when it comes to scale, fill, gradient, colors and break, we already redefined them. What we need to do here is change actually this one, and we need here the average DF and the mean. So these are for the limits, and we can just copy and paste it here also for the maximum value. Of course, we are not doing the panel map here, so we can just simply remove this line. And then for the guides, everything remains the same, and also the theme for the wind. So once you actually run this whole chunk, you should be now able to see only one map, so that shows the average precipitation levels for Switzerland from 79 to 2022 inclusive. In this section, I will show you how you can leverage the power of rayshader to turn your 2D contour map into a 3D map. So we start off by calling rayshader and then the plot gg function, which turns your ggplot2 objects into 3D objects. So here we pass the map2 object. And then we also define the width and the height in inches. So this should be a lower number. I went for the option of 7 by 7 inches. You might consider even lowering this one to make rendering smoother, faster. And the next thing we want to define here is what is the height of the spikes. The default version is 150. I'm going to go for a higher 250. It's not very intuitive, so you really need to try this. So the next thing I want to do is I want to disable the solid part here around the map, and I don't want to have the shadows of that plane around the map, but I do want to have the shadows. So I'm going to actually turn on the shadows here. So shadow equals true. And once we actually define this, we can also define things like, for example, shadow color. What I like to do when it comes to shadow color, I would like shadow color to define as white, because then the shadows behind the object are not as dark as they can be. So shadow color, and I also like to really decrease the shadow width. Shadow width, I just put it to 0 here. So making sure that really the shadows, they do exist, but they're not so stark. And then here for the shadow intensity, I put the value of 1, which means the lightest possible shadows, right? And we can also define the window size here, or we can just go for, the default window size, but I like to define the window size. And this one, what is interesting is this one is in pixels exactly. So I just go for, let's say 600 by 600 pixels. So it's not a big one. You can also define, for example, the zoom levels. So for the zoom levels, you either go from 0, which is completely zoomed in, to 1, which is completely zoomed out. I'm going to go for, let's say, 0.7. We can then see whether it works for us, whether we can see the whole picture. And then this is then the degree. So this is the degree that the map will have. So for now, I'm just going something closer to the normal degree. So the outlook of this map, for now, the render scene, it's going to be more like a 2D. But then I will show you how you can actually choose a smaller degree to make it like to have like a perspective here, right? And then also there is a theta argument. This is how much this is tilted around your Z scale. We will also play with this one, but for now, once you actually run this, you should be able to see a render scene that looks pretty much like a 2D map. But in the next step, I will show you how you can re-render this scene and how you can like put it in a bit of different perspective. So as I said, I would like to make this one to turn the perspective so that we have this 3D look. Currently, it doesn't look like it's gonna have a 3D look. And you can easily change this and play with this using the rayshader or render camera function. So over here, you can actually change 3 arguments. The first one is the zoom level. So for now, we're just gonna keep the same zoom level, and I'm not gonna touch that. You can change the degree of rotation, of course. So I choose, for example, now 60 degrees. So I'm gonna have it under a sharper angle. So this is gonna make sure that the spikes will be visible once we render them in 3D. And the second argument I want to change is this theta. So how much is this tilted around the Z scale? And over here we chose 0, so basically it was just like a flat orientation, but I'm going to choose here 30, so this is also going to change it a bit. And now once you actually run this, you will see a new render scene with a bit of different perspective, and now you can clearly see not just Switzerland itself, but you can also see the spikes. The next step is to render this 3D object and save it locally. And our final step in this journey is to render this 3D object. And this we will do using a render high quality from rayshader. So over here, we need to define the first of all, if we of course want to save it as a local file, what is it gonna be called? So we can just call it Switzerland average precipitation. And of course, it needs to have here an extension. So I'm gonna go for the PNG extension. That's the first one. I will also turn on the preview as it renders so that you can see how this looks like. I'm gonna go ahead and turn off the interactive part where you can actually also move the scene as it renders. Of course, I'm gonna utilize the fact that I have parallel course here, so the parallelism. And then I also want to include the lights here. Now for the lights, I'm going to use the one that I used in previous tutorials. I really like this source of light. It's environment lights. It's an HDRI file, which I downloaded from a very cool website. And I'm going to put the link in the description box. And I'm also going to include this file in the GitHub repo. So you don't need to worry about that. Well, for now, it's just like for your information, it's called Air Museum Playgrounds. And then importantly here, okay, also 4K. Importantly here, it's HDR extension. So Air Museum Playground 4K HDR extension. Again, I will include this one in the GitHub repo. So here you can choose what is the intensity of this light. I often find this light quite strong, so I tend to decrease the intensity. So let's say 1 will be a default one. So if you decrease then the value to, let's say 0.45, then this would be, let's say 45% of the strength of that, default light. You can also rotate this one. What I do like to do about this is to always have the shadows somewhere in the southeast perhaps. So that would mean rotating this by 90 angle degree. And then you can also here define the width and the height. Let's say, for example, 2000 by 2000 pixels. This is not going to be a very detailed map, but if you want to make it more detailed, you can definitely increase this. And this is going to render, I think, in a very few minutes. And that's all for today, folks. In today's tutorial, you learned a few valuable lessons: how to access 1 out of 27 precipitation datasets in R, how to do some data wrangling, and then how to create some really cool 2D and 3D contour precipitation maps for Switzerland. I'm really looking forward how you can take this tutorial on a journey across the world and create some other awesome precipitation maps for other countries and regions. If, however, you are interested in replicating today's analysis, I prepared the link to the GitHub repo in the description box below, together with some other links, so do check it out. Feel free to clone it, modify it, reuse it as you see fit. If you have any questions, comments, or just general feedback, feel free to reach out to me on YouTube, but also on X and Instagram. If you're new to R and you seek to expand your data visualization and geospatial knowledge with R, I prepared a few cool tutorials for you, so do check them out. See you next time.